Good morning. Uh, Before going on with the new topic concerning the application of the semi-classical equations of motion when we have both an electric field and a magnetic field applied to the system, I would like just to add two comments concerning what I told you during the last lesson. In that case, we obtained that let's say after the calculation of the period required for the electron to complete one orbit, we obtain a value for the effective mass of the electron, and that value was h bar squared divided by 2 pi times, if I remember correctly, did I use the symbol delta A, yeah, divided by delta E. So a small variation of the extension of the area enclosed by the Fermi surface divided by the small variation of energy concerned with the slight deviation from the orbit using the vector delta K that was in the plane orthogonal to the magnetic field. If we just try to evaluate this expression when we have free electrons, in case we have free electrons, the energy of the electrons, so just in the, let's say, in the free electron case, then the energy is equal to h bar squared times the square of the wave vector divided by twice the mass of the electron. And if we consider the area, since the Fermi surface is a sphere, the shapes of the orbit are circles. So the area of a circle, if we suppose to consider a circle that is in the, let's say, xy plane, yeah. So in the maximum area of the circle that can be included by the Fermi surface, then this is pi equal to pi times the square of the wave vector that indicates the circle where we have the orbit. If we consider just a small variation of the energy and of the area, we have that dE is equal to h bar squared divided by the mass of the electron times k dk, and the small variation of the area is equal to pi times 2k dk. So if we try to use those two expressions to evaluate the effective mass, then we have that the effective mass is h bar squared divided by 2 pi. Then we have a small variation of the area, so we have pi times 2, and then we have k dk. And the small variation of the energy is h bar squared divided by the electron mass, and then we have k dk. This 2 pi can be simplified with the 2 pi that was the initial coefficient. Then h bar squared can be simplified, and also k dk and k dk may be removed. So at the end, we have just the rest mass of the electron. So in the case of free electrons, the m star expression reduces to the rest mass of the electron. In case we do not have free electrons, but we consider block electrons, then m star is just the effective mass that enables us to consider the electron as if that was a free electron with just a modification of the actual value of the mass of the electron itself. So this comment was just to see that if we try to use this expression for the effective mass, we actually obtained at least the rest mass of the electron in the free electron picture. Then, as we saw for the last comment was about the fact that when we consider the effect of an electric field to the motion of the electrons, we saw that it was possible to use two different pictures. One picture was one concerning the motion of electrons, so the motion of the occupied levels, let's say. The other picture was the one concerning holes, the motion of holes, so the motion of positive particles that are related to the unoccupied levels that we have in the system. I just wanted to see that the same picture can be obtained when we consider the application of a magnetic field. For instance, the two examples that I had in mind are the following. If we consider situation one, and situation one is this one here, so we have the electronic levels. I always use the nearly free electron picture to make the Venn diagram. So if we suppose that the electronic population is close to the minimum of the band, so that the Fermi energy crosses this, in this case, the first band, and the energy versus wave vector dependence that we have here is very close to a parabola, so the occupied levels are close to the center of the first Brillouin zone, and this is the, let's say, the one-dimensional representation of the system. If I make the 2D equivalent of that, in the 2D equivalent, we consider that the first Brillouin zone, always in the simple cubic lattice approximation, is a square. And if the occupied levels are the levels close to the center of the zone, then we have that the occupied levels are the levels enclosed in this area, in this circle. So in this case, we have that the occupied levels are within that area. If we, for instance, consider one electron here close to the Fermi surface, we may see just what happens when the Lorentz force is applied. So when we apply the Lorentz force, we have that in this case, the expression is minus C vector product by the velocity and the magnetic field. Since the velocity is proportional to the gradient of the energy, then for this electron, the gradient of the energy points outward with respect to the Fermi sphere. And if B is applied orthogonal to this plane in the vertical direction, if we make the vector product, we have V that is going out with respect to the sphere. Then we have B that is vertical, the minus E in front due to the negative charge of the electron. So what we obtain is that the, that K prime as H bar K prime is equal to minus C do vector B. Then we have that the motion of the electron in this case is counterclockwise. So in this representation, the electron moves as we, let's say, expect in case we have a negative particle. If we consider situation 2, and in situation 2, we have, again, in the one-dimensional representation, that the occupied levels So if we suppose that the Fermi energy crosses the electronic band structure close to a maximum, so in this case, the occupied levels are not close to the center, but the occupied levels are close to the border of the zone. And if we use the 2D representation, we have always the, let's say, the first Brillouin zone that is a square. In this case, we have that the occupied levels are the levels that are in this area. Because now the occupied levels are not, as it was before, close to the center, but are close to the border of the zone. So if we now pick up one electron in more or less, let's say, in a position that is close to the initial configuration, in this case, the speed is always the parallel to the gradient of the energy. As you see here, in the one-dimensional diagram, the gradient points in the direction where we have an increase of energy. In this case, so the energy increases if you approach the center of the zone. So in this case, the gradient points towards the center of the zone. So this is the, let's say, the velocity of the electron. So the velocity has this direction. If the magnetic field is always applied in the plane and is directed, so is orthogonal to the plane of this diagram, then if we again use the vector product between velocity and b to take to estimate the equation of motion for k, then we have that the k prime variation is in this direction. So if you compare the two diagrams, in one case we have a counterclockwise motion. In the other case, in this one here, in situation 2, we have a clockwise motion. So simply changing the occupancy of the levels, we have that in one situation, we have the motion of a negative particle, let's say what we expect when we apply a magnetic field to an electron. In the other case, due to the change of the occupancy of the levels when we are close to maximum, we are in a situation where the orbit, the circular orbit of the electron is opposite with respect to the circular orbit that we had before. So in this case, it's just like as if we had changed the charge value of the electron. So in this case, we have a negative particle. In case that was labeled as 2, we have the motion of a particle that seems to be positive for what concerns the charge. So in this way, I just wanted to recall that the same modification of the charge value of the electron, let's say, that was observed in the case of the application of the electric field can be also obtained or observed when we consider the application of the magnetic field. So in both situations, we have this, let's say, electron representation or the Hall representation according to the occupancy of the bands in the system we are considering. Okay, so after these two comments, I would like to go on with the next step. And the last step of the calculations is the situation where we have the simultaneous application of an electric field and a magnetic field. And the configuration of the fields is always the same that we used in the case of the Drude problem when we try to investigate the presence of the magnetoresistance, and also when we try to evaluate the Hall coefficient. So the idea of the calculation is to evaluate RH, so to evaluate the Hall coefficient and to determine whether the system can or cannot display the magnetoresistive effect. So the dependence of the resistivity of the system on the magnetic field, a phenomenon that was observed in the lab but was not explained by the models of Drude and of Sommerfeld. So in this picture, we always have to consider the semi-classical equation of motion, so the derivative of the speed of the position vector is equal to the speed, and that the derivative of crystal momentum is minus C electric field plus the vector product of V and B. This equation resembles the equation that we obtained, that we used when we described the effect of just the application of a magnetic field. In that case, as the velocity is proportional to the gradient of the energy, since we had just this vector product here between V and B, we were able to say that the orbit of the electron was included in a plane that was orthogonal to the magnetic field, and we could also say that the orbit of the electron in the reciprocal space was orthogonal to the energy gradient. So the orbit was on a circle, on a path where the energy of the electron is constant. In this case, since in the Lorentz force we have also the presence of V, of the electric field, we may not use, in principle, we should not use the same approach. So at this point, we may not say that the orbit is on a constant energy surface and that the orbit is orthogonal to the gradient. But to see whether we may just use the same approach even as a first approximation, we may try to rewrite this equation of equation of motion of K prime, trying to, let's say, recover an expression that was similar to the case where we had just the magnetic field, even in presence of the electric field. So the idea is to keep this vector product with B and try to rewrite E so to have the same structure. So something including E times the vector product with B. Taking into consideration the fact that E and B are orthogonal with each other, we may do something similar we did during the last time. So we may apply first a rotation of E using the versor of B, and then we may rotate back everything using B. So in this case, we have something that is equivalent to the initial expression, but now has this vector product with B. Due to that, we may collect the vector product with B and rewrite this as minus E. Then we have B versor vector product E. Then we have plus 1 divided by h bar, the gradient of K of E of n. And then we have at the end the vector product with B. The idea is now to take this constant term here and take that into the gradient. So to obtain that, we have minus C, then 1 divided by h bar, the gradient as a function of K of, we have B versor vector product E. Then we have to multiply by h bar, as we have taken h bar out of the parentheses. then if we want that the gradient of k of this term is equal to B vector product E, we have to multiply by k. So in this way, we have the gradient with respect to k of this expression. So at the end, we have just the constant term. And then we have the energy. And then the vector product with B. So this expression can be written as minus C divided by H bar gradient with respect to K of this, let's say, effective energy, where the effective energy is equal to H bar B versor vector product E times K plus the energy that we had without the contribution of the electric field. If we consider this value En of k, En of k in general is of the order of EVs. So more or less E of n is expected to be of the order of some EV. What is the order of magnitude? So this is of the order of EV. What is the order of magnitude of this part here? H bar is the Planck constant divided by 2 pi. B versor gives no contribution to the modulus. E, if we take E equal to 10 volts per meter, and we, just to estimate K, we use 2 pi over A, so the size, let's say, of the first Brillouin zone, and we use as an estimate of A 3 angstroms. And what we have, if we include all the values in this expression, we have that the modulus of this term is of the order of 10 to the minus 4 EV. So the conclusion is, even if we have an electric field now in combination with the magnetic field, so in principle, we may not say, by looking at the first expression, at the initial equation of motion of the wave vector of the crystal momentum, sorry, that the orbit, that the motion of the crystal momentum is in an orbit orthogonal to B over a constant energy, and with the constant energy. By considering this new representation of the equation of motion, and considering that E of n is at least 4 orders of magnitude larger than the contribution of this term here, we may again consider that the electronic orbit, so the trajectory we consider that the K trajectory is again orthogonal to B and is over a constant energy surface, and this is so as a first approximation, we may say that the orbit is in the plane orthogonal to B, so we have to consider the intersection between B, the plane orthogonal to B, and the Fermi surface, and then we also consider as a first approximation the fact that during the motion of the level, then the energy along the trajectory is nearly constant. So using this first approximation, we may consider that the structure of the orbits is the same that we obtained in the case where just the magnetic field is applied. So we have also in this case two different groups of orbits, of trajectories. We have closed orbits and open orbits. So the same situation that we had before when we consider the contribution of the of just the magnetic field. So this first part was important to say that the same approximations concerning the shape of the orbits that we did in the case where just the magnetic field is applied can be now used when we consider the mutual application of an electric field and the magnetic field that are orthogonal with each other. So in this case, the first step is to rewrite the equation of motion of the crystal momentum, so to consider the the connection between the orbit of the electron, the orbit of the level in the reciprocal space, with the orbit of the same level in the direct space. And if for you is fine, as the calculation is exactly equal to the calculation that I presented to you when we consider just the application of the electric field, of the magnetic field, if for you is fine, I just write the final expression of the calculation. So the idea is always to multiply everything. So the equation is h bar k is equal to minus e times e plus velocity that we may write as in the previous case as the derivative of the position vector product p. So the idea is always to multiply both parts of the equation by b versor. So b versor, then we have the vector product with h bar k prime, and this is equal to minus e b versor vector product e, and then we have minus e b versor vector product by r prime vector product b. And if we just expand, the only point that we may modify is this one here, and this is exactly equal to the one that we observed when we just consider the effect of only the magnetic field. So the final point is that the as in the previous case, we are left, due to this double vector product, we are left just with the component of the position vector that is orthogonal to the direction of b. So at the end, the equation of motion for the position vector is r orthogonal at time t minus r orthogonal at time 0, and this is equal to minus h bar divided by e b modulus versor b vector product k at time t minus k at time equal to 0, and then we have plus e vector product b versor. Here, in principle, in the calculation, I didn't have the e versor, but I had the e vector. Just to distinguish the versor from the vector modulus, I just write e as, so e is e versor times e modulus. So here I leave just the versor and I take the modulus of e here, then I divide by b modulus times t. So this b modulus comes from the, at the end of this part of the calculation, we have position vector times B modulus, then I divide everything by B modulus, so I have one B modulus here and one B modulus here. So this is the equation of motion. The first part is equal to the part we observed during the last calculation. In this situation, we have an additional contribution. And if you notice, if you just consider this part here and this part here, you have that this is a sort of straight trajectory motion. So we have that the variation of the position vector is related to a constant term here that depends on the modulus of E and on the modulus of B times T. So it resembles a linear motion over a straight line. And in general, this part here, so the constant speed is labeled as W and is called drift velocity. So drift velocity is given by E versor product B versor times modulus of E divided by modulus of B. And if you notice, this velocity is orthogonal to E. So in this case, the typical velocity of the electron is not parallel to E, but is orthogonal to E. So in the case that, and I will now in a while I will comment on that, is this, if this term is the leading term, then the motion of the electron is not along E, but is along a straight line that is orthogonal to E. And to be able to say something more concerning the effect of this equation of motion, we may consider, as we did in the case of the application of an electric field, that the electron during its motion suffers collisions. So we have to recall that we have collisions. So as the typical average time between one collision and the next collision is given by the relaxation time, we may say that the, let's say, a representative value for T in this equation is the relaxation time. So on average, we expect that the effect of the electric and magnetic field can be described by this expression. Okay, we may divide everything by the relaxation time. So if we, at this point, we may simplify the relaxation time . Okay, so what we have here is that if you notice, this part here is a sort of average velocity. So since you have at the numerator the distance that is traveled by the electron from t equal to 0 to t equal to the relaxation time divided by the relaxation time. So this is again sort of average velocity. I would like to have now a comment concerning the what I will do from now on. In general, it's difficult to, let's say, find the full expression of the electron trajectory considering this equation of motion and considering the fact that we may have both closed orbits and open orbits. So what is generally done is to use this equation as a starting point of the calculation, then to apply some approximations and obtain just a qualitative indication of what you expect to observe in case you have open orbits and in case you have closed orbits. So the idea from now on is to, let's say, considering two different scenarios. In one case, when we have open orbits, in the other case, when we have closed orbits, and in each scenario, we consider the approximation that allows us to simplify the formalism and to just obtain an indication of what is happening in that case. So from now on, I will just rely on a couple of approximations that I will use in the open orbit case and in the closed orbit case. So let's start with the open orbit. Sorry, let's start with the closed orbit, that is the more similar. So closed orbit means that whatever the shape of the orbit is always within the first Brillouin zone. So k of tau of relaxation time minus k0, the modulus of that has an upper limit. So if you consider, for instance, just for simplicity, a circular trajectory, this delta k at maximum is the diameter. So the delta k will never be larger than the diameter of the circle. So this is the idea of this delta k max. It's just to say that you have an upper boundary here. If we have an upper boundary and we suppose that tau, we may send tau to infinity, or in general that tau may be very large. What is the physical motivation behind that? The physical motivation is that you have a very pure sample, so no defects, no distortion of the crystalline structure. You are nearly close to the perfectly periodical lattice where the electron may move, in principle, with a very, very high conductivity. And if you remember, in case we consider this approximation, so if the relaxation time is very large, it is also fine that omega c times relaxation time is larger and larger than 1. And this is the same approximation that we used when we evaluated the dielectric constant in the Drude case. So this means that during one relaxation time, the motion of the electron is able to describe many, many orbits. So this means that the electron strongly feels the effect of the magnetic field. So in this condition, due to the fact that if you consider this fraction, at the denominator, you have the relaxation time. At the numerator, you have delta k. Since delta k is bounded because we have this condition here, if the relaxation time goes to infinity, then what we have is that this term here can be neglected. So in the case of closed orbits, this term can be considered to be nearly equal to 0. So we have that the average velocity is equal to W, so to the drift velocity. And if you, yeah, just a comment of the meaning of drift velocity. No, one step back. So in this case, we have that the electron describes a trajectory, and this trajectory follows the direction of the drift velocity, and the drift velocity is orthogonal to the electric field and to the magnetic field. And if we now recall the definition, since one of the aims of this calculation is to obtain the value of the Hall coefficient, the value of the Hall coefficient was related to the ratio between the electric field orthogonal to the current divided by the current and divided by B modulus. So at this point, we just have to evaluate the density current. So we have to evaluate J. In this, to evaluate J, we may use the fact that as the average velocity of the electrons is given by this expression, we may use the expression that was adopted by Drude. So we have that the current density is minus E times electronic density times the average velocity. So in this case, this is equal to minus E electronic density and the velocity, that is E Versor vector product B. Then we have E divided by B. So this is the expression of the velocity. So at this point, it is possible to evaluate RH. So what we have is, now the current is proportional, sorry, the current is orthogonal both to E and both to B. So if we look for the electric field that is orthogonal to the current, the electric field orthogonal to the current is exactly E. So here we may write E. Then the current is minus E and E divided by B, and this is, sorry, E modulus, E divided by B, and then I have to divide by the modulus of the magnetic field. So this is equal to minus 1 divided by NA. Please, so, and this is the final result of the calculation. Please consider that if the Hall's approximation had been used, the final result would have been 1 divided by NE, where N is the Hall's density. So this indicates that, let's say, what may we say about this expression? On one side, if you notice the expression of the drift velocity, the drift velocity is not parallel to E, but is orthogonal to E. So the conclusion is that when you have an open orbit, you may still have a motion that is along a straight line, but in this case, the effect of the magnetic field is so strong that the direction of motion of the electron is not parallel to E, but is orthogonal to E. So you have a motion that is not in the sense of the field, but is orthogonal to the field, to the electric field. And then concerning this and the electron density, and also concerning the Hall's density, Both values are not the values that were used by Drude, both due to the fact that in the case of Drude we didn't have holes, but in particular due to the fact that the electron density and the holes density comes from the evaluation of the comes through the evaluation of this integral in the case you consider electrons. In the case you consider holes, you may do an integral that is similar to that, but in this case, if f tells you what is the average probability to have that level occupied, 1 minus f gives you the average probability to have that level unoccupied. So in the case of holes, you just consider unoccupied levels. In the case of electrons, you consider only occupied levels. So in this picture, n is it comes from the evaluation of this integral. So if you consider the case where you have occupied bands and also not completely filled bands, the electronic density that you have to use comes just from the unoccupied, from the bands that are not completely filled, not from the bands that are occupied. So in this case, n can be smaller, for instance, of the value that was obtained by Drude. So one comment is the value of n that you include here, or the holes density that you include here, are not obtained as an a priori indication, but are obtained as due to the evaluation of these integrals here. So they may be different from the values that were obtained by Drude. Then if you have, for instance, if more than one band contributes to conductivity, the full value of RH comes from the contribution of all the bands. So you have the contribution of one band and the contribution of the other band, where this is the first band that contributes, and this is the second band, for instance, that contributes. In particular, if you use the, let's say, electron approximation for one band and the holes approximation for the other band, you may also have, for instance, so depending on the approximation you want to use for the calculation, you may use the minus or the plus sign, again, depending on which approach you want to use. If you want to use the electron approach or the hole approach. Both the comment concerning n, so the value of the electronic density, and the comment concerning the fact that the final value of the hole coefficient comes from the contribution of all the bands that are involved in the conductivity phenomenon, gives us at least an indication of the fact that the strange values of RH that we obtained in the Drude case, in particular the fact that in some situations the Hall coefficients could also be positive and not negative as Drude expected, may be due to the fact that maybe one or all the bands can be in some specific situations populated or described as if they were populated by holes. And in that case, what you expect is to have a positive coefficient. So the fact that the coefficient may change from negative to positive depends on the fact that maybe in some systems, due to the electronic density, the actual charge carriers are not electrons but are holes. So in that case, a positive value for RH is perfectly fine, since we know that in this formalism, the value of the charge of the sign of the charge carriers can switch from negative to positive. So this just qualitative these qualitative indications concerning the value of RH and the sign of RH somehow reconcile the Drude results, the experimental results with the results that may be obtained by this model. So in general, this is an indication that the values that we may obtain, we may observe in the lab, are not said to be negative, always negative. So they may also change sign. And I would just like to finish the calculation. So then after the break, I will comment also on the presence of open orbits. So I would like just to conclude before the break, only the calculation in case we do not have open orbits, but we have closed orbits. So in that case, so if we have open orbits, the equation is always the same. So the initial equation is R orthogonal at time equal to relaxation time minus R orthogonal at t equal to 0 is equal to minus h bar b versor. Then we have k of relaxation time minus k 0 divided by the relaxation time e b modulus, and then we have plus drift velocity. So if we suppose to be in this configuration, so open orbits that let's say may reach the second and the third zone starting from the first zone. So we have orbits that are describe the possibility to propagate the orbit through many zones belonging to the reciprocal lattice. If in this condition we suppose that B modulus grows to infinity, so we have very, very large values for the magnetic field, as the drift velocity is equal to E product with B times E modulus divided by B modulus. In this approximation, the drift velocity is expected to go to 0. And if you notice here, we have in the second part, sorry, I forgot the relaxation time here. If we consider this second term, we have B that goes to infinity. But if you remember the equation of motion for K, that was minus E times 1 divided by h bar, then we had the gradient of the effective energy vector product B. So this means that the rate of change of K is proportional to B. So if B goes to infinity, so if B increases and is larger and larger, also this difference, so if B goes to infinity, also K of relaxation time minus K0 increases accordingly, as the derivative of K is proportional to B. So the larger the value of B, the larger the value of K prime, the larger the variation of K. So we may not suppress this term anymore, as the upper part of this term here, K of tau minus K of 0, may now increase as we consider open orbits. So in this part, the only term that is suppressed is the term of the drift velocity. So the final expression is that R orthogonal, the variation of R orthogonal divided by the relaxation time is minus H bar B Versor vector product K relaxation time minus K0 divided by relaxation time EB. So what is the final comment here? If we, let's say, if you remember the diagram that I showed you last time, the open orbit appears when we consider NEX. I just now make a two-dimensional representation of this phenomenon. So if we have, for instance, a neck so we have a deformation here of the Fermi surface, and the Fermi surface reaches the border of the zone. So we have another so if the electron, if the starting point of the electron is here, and if we suppose that due to the equation of motion, then the trajectory follows this path here, what we have is that as time increases, the trajectory of the orbit follows the intersection between the plane orthogonal to B that crosses the Fermi surface in correspondence of this point and the Fermi surface itself. So we have this sort of, in this picture, ondulation that propagates in the reciprocal lattice along this direction. So the idea is, if such a structure is observed in the reciprocal space, in the direct space, what we have is that the initial trajectory is just rotated to obtain the final trajectory in the direct space. So if the motion of the electron takes place along a given direction, then just rotate that by 90 degrees, and then you have the corresponding trajectory in the direct space. Now, this is not actually a straight line. This is, let's say, an ondulation with an average, along an average direction. But if you consider this as a very rough approximation to be a straight line, then we may say that in the direct space, the orbit takes place along a straight line that is orthogonal to that. So in the case of open orbits, using this, again, rough approximation, we may say that the motion of the electron takes place so there is a specific, a peculiar direction along which the motion of the electron takes place. So we may approximate, again, using very rough approximation, the actual trajectory both in the reciprocal space and in the dark space as if that orbit was a straight line. But this is just to say that with respect to the previous situation, when we have a motion that is not circular but is along a closed orbit, as we expect for a charged particle when a magnetic field is present. In this case, due to the structure of the energy in the reciprocal lattice, what we may have is that the orbit is not a closed orbit, but develops along a sort of straight line in the direct space. Again, what I have just presented you is just a very, very rough approximation of the electronic motion due to the fact that to handle the full, to investigate and to study the effect of the full equations is not easy. So in generally, what is done is to make those approximations to simplify the problem to the core and just see what happens when we use this strong simplification. Okay. So since now I would like to add some comments concerning the effect of this specific orbit in the dynamics of the electron, I think it's better to make the break now, and then after the break, I will go on and comment on the effect of this kind of orbit on the electronic motion. So for the moment, I stop the registration, and then I go on during the second part of the lesson.